Right, good morning. It seems like we reach a steady state of no more people coming. So good morning, everyone. My name is Frank Munz. I work for Databricks. I was actually here last time, like the first time at Vox Days Ticino, pre-pandemic, maybe 4 or 5 years ago. It feels like a decade ago. And that time I had a presentation about scaling CPUs, and I think the talk was like, what would you do with 1 million cores? And everyone was like, isn't that marketing? Who's using 1 million cores? And the summary, the TLDR of the talk was, yeah, there are a few companies who do this with special software on one particular cloud provider for a special use case. Now, here it says data and compute is what I'm doing, so I work for Databricks now. Now, this talk is the opposite. It's not about large-scale compute. It's about large-scale data. This is what Databricks is doing. So we like to call ourselves the data, analytics, and AI company. And there is a statistics out, a research paper, I think by Forrester, where they say 73% of all data becomes dark data. Dark data is data that is not used for decision making. So you basically acquire it, you store it, but you never process it in a meaningful way. So this talk is about large-scale data, about processing data in a more modern way. And it's also about streaming data, because this is what we see more and more in our workloads, how people process streaming data. And it's also talk about the Lakehouse, which is a new concept in data management systems. So I'm on Twitter if you want to connect. The talk is really packed, so if you have questions, please keep them to the end or stop me for a coffee and we have a chat then. Can I have a raise of hands who's using Apache Spark or who knows about Apache Spark? Oh yeah, that's quite a few people, that's good. And there's more people coming, cool. Excellent. What is your favorite thing about Apache Spark? I remember when I started doing this like years ago, and I took a course, and when I took this course, I thought like, wow, the really cool thing that caught my attraction, first of all, was like how easy it is to ingest a couple of JSON files, where each JSON file, again, contains a couple of data sets, and then you have your data frame, and you work with this, and you find out all the customers that drive a particular car make. And so like, wow, this is so good compared to the, apologies, I know it's a dev conference, the fiddling you do in Java or to whatever we had to do for the old people like me in Perl or in Python without any libraries. So this was the first thing when I thought like, this is really nice, this is really helpful. And then if you have like a notebook that supports SQL as well, you just switch from one cell to the other cell. And in the next cell, if you execute this create or replace temporary view statement, you can type your SQL. Now, I'm not an SQL person, to be honest. I have more a dev background. But I'm a very convenient person. So I love to be able to switch from Python to SQL if SQL is the easier solution for me. And being able to do this within one notebook, I thought, this is so cool. Like, I mean, this is what I want to do. Yeah, and then the other thing, thinking back about the other talk I did like 5 years ago when I told you, look, you might get 1 million CPU cores, but then how do you program them? What do you do with them? And I told people like 20, 30 years ago, I was working in research and we did functional imaging of brains, but the way to program these applications was to do explicit message passing with MPI and PVM. So the developer had to parallelize the program and to send the data to the remote jobs and to make sure you care for those cases when a remote job dies and all this. So a lot of explicit manual parallelization of programs. And if you run such a Spark statement, the cool thing is SQL, first of all, but then behind the curtains, it's automatically distributed. And a lot of people start using Databricks and notebooks, and they type stuff, and they don't really appreciate the beauty of having this automatically distributed and executed in a very performant way on cheap, custom hardware, or in the cloud on cheap cloud instances and spot instances, and using all the modern Graviton processors. etc. And obviously, you get the same result. Now, I told you this is about streaming data. So talking about streaming data, just a side story. I did a Kafka tutorial in my previous job, and this reached now like 50,000 views. And like every 10 days, someone is sending me a Twitter message, and they say, hey, Frank, can you help me writing a Kafka client in, well, pick it, Python or Java or JavaScript or whatever. And I would think like, well, Google it, obviously. And then I think like, how would you do that in Spark? What's the difference between reading a file and connecting to Kafka or Kinesis or to a socket? Well, the difference is here. It's the read becomes a read stream, and then you say format Kafka, Kinesis, whatever, and you read a stream. And then the other cool thing is you go back to your same data frames and you work with the data frames that you already know from the static, processing. So it all works nicely together. And if we think about stream processing, the big difference is compared to batch, where you have a data source and you collect the data in some storage area in some directory and it piles up. And then maybe every Friday you run your batch job that creates a data for a BI dashboard. It's this two-step process, It's like one-off and bounded. You collect the data, and then it's a second step. And if you compare this to stream processing, it's more continuous. It's unbounded data. That's a classical characteristic of streaming data. And you continuously process this data. There's obviously lots of technical advantages. I think the first one is the important one. It's a more intuitive way of dealing with data. Why would you wait? Why would you store it first and then at a certain time process it if you could do it otherwise? If you continuously process it, you should be able to have lower latencies. Because you continuously process it, there must be some checkpointing because somehow the system needs to remember what you processed already. So there is a built-in better fault tolerance. And at the end, if you had to design a system that runs a huge batch job every week or every month, how would you plan for the resources? I mean, you need to execute this huge batch job as a spike. It's like a spike in CPU usage. It's easier these days in the cloud, but still you need to provision for this and plan for this somehow. If you have this streaming approach, it's a continuous use of your computing resources, and it's much easier. Okay, but there's also a couple of misconceptions. And the first one is that streaming is only for low latency. And I hear this a lot from sales and from marketing sometimes. They say, well, streaming, real time, low latency. And that's not necessarily true. You can actually use this streaming approach and see batch as a special use case of streaming, especially if you go to Spark Structured Streaming. You could say, read stream, and then give me everything that is available right now, everything maybe that piled up since last Sunday or in the last whatever, everything that is available now. The other misconception is it's kind of like the, sometimes call it the poor man cap theory. Do you know the cap theory? Yeah, you nod, you're experts. I have a shoemaker next to my house, and he says, I know you want high quality, you want it cheap, and you want it now. Pick two of those. And that's the same thing here for streaming data. People think, well, we need the lowest latency. Ask anyone who designs a system. Yeah, it should be, it should update the BI dashboard in less than a second. And you say, well, I can design you that system. Are you willing to pay for it? They say, well, can we change that less than a second to maybe once a minute? And then how much does it cost now? Like using resources. So latency, the lower the latency is not always better. Many business use cases just don't justify it. And then the other thing is accuracy. If you have super low latency, how do you deal with late arriving events? If I want to have, like from 1,000 of measurement stations in Switzerland, like traffic changes, and I want this per second, but some of those stations send those events later. How do you deal with late events? it gets more unprecise if you increase, if you decrease the latency And the other thing is cost. Obviously, we can build systems with like super, super low latency. And I kind of think if we talk about real-time systems, and that's also some marketing or some sales thing, like calling it real-time, but real-time with a guarantee that it's executed within that time frame is, what my grandmother has in her heart pacemaker, or what you have in the ABS system or in the traction control of your motorbike. Do we need this? Very often we don't need this. You can get it, but it comes with a cost, and sometimes it also comes with a change in technology. So those people that build heart pacemakers, they are not using Java because, of the latencies and garbage collection. We all know this, although I know it's getting better, and no offense, by the way. But lower latency is not always better. It's more like, are you able to tune it in a way that you get to the latency that you want within an acceptable cost range? So the summary here is that streaming is more about the programming paradigm. You process it as it arrives in a way that is not kind of the batch way where you store it, you look it up, what you have, and you do this one-off thing. And I think one of the most popular, maybe the most popular systems for this is Spark Structured Streaming. It's a scalable and fault-tolerant stream processing engine built on top of Spark. There's a new project coming out, or it's actually, we're in the middle of this project. It's called Project Lightspeed. Maybe a bit of background. Databricks, the company that I work for, was founded by 7 people, and one of them was the original creator of Apache Spark. The other popular open source projects that we made open source, one is MLflow, and the other one is Delta Lake. I come back to Delta Lake as well. And we're working, one of our key engineers is working on Project Lightspeed right now, where they try to get predictable low latencies for Apache Spark. And I come to this in, let me see, actually in a few slides, and explain you why this is important. So structured streaming in Spark, you need a source. You read from a source, like you read from Kinesis or you read from Kafka. And then the system needs to remember an offset position and track this offset. There will be some transformation because that's typically the purpose of what you're doing. You have some raw data, but you need to process this in a certain way. You need to drop columns or rows if you have this tabular view. And then there's this thing, the data needs to go somewhere. I mean, that's the thing, like where do you put it? There will be a target, and then you need to write checkpoints for that target. And there's a trigger that defines like how often do you want to run this. Looking at code, kind of looks like this. This is the source. Read stream from Kafka, Kinesis, socket. And then there is some transformation in the middle, like a select. Maybe select with a where statement. There is the sync, where you write it to write stream, and you define. I'll explain the format delta. It could be something else, but we often use the delta format. And then there is this configuration, like you trigger this every second. And benefits are it's unified for batch and streaming. It gives you high throughput at a low cost. And this is the interesting part. Where's the latency? I mean, this is where we're working on getting lower predictable latency, but it's optimized for throughput and cost. If you ask business people, like probably 8 or 9 out of 10 would say, well, I want throughput, I have massive amounts of data, and I want this at a lower cost. If you can give me the same thing for 50,000 cost of resources, cloud resources, instead of 100,000, I take the 50,000 per month, and my boss will be super happy because I saved him 50% of cloud spend. And then it comes with exactly one semantics, and there's a rich ecosystem of connectors. Right. Now, the talk is about streaming data in the Lakehouse. And now a lot of people say, so what's the Lakehouse? Tell me, what is the Lakehouse? Well, to explain you the Lakehouse, let's look at this data maturity curve. It's an easy curve. Actually, everyone who's doing fancy stuff wants to be at the right end of this curve. People want to do AI, machine learning, forecasting, prediction, all the fancy stuff. So they want to be on the right end side of this curve. And typically the data management system they have is a data lake. They dump a lot of data in S3. That's the data lake. They hope that it doesn't degenerate in a data swamp. And they want to run data science, machine learning applications on top of this. But they cannot completely move to the right because they still have the thing on the left, which is the data warehouse. Now, sometimes in these talks, it seems like this is the old thing that we want to cancel and give up. You can't. You can't because this is where the key data is coming from that your CEO, your chief financial officer, whoever needs to see. So if they trust one thing in your company, it's the data warehouse, and the dashboards generated based on data in this data warehouse. So people have both of these systems, although they would like to move to the right, which causes a lot of problems because you have two stacks, two different teams, two different skill sets. And then it's actually not two separate data sets because people start copying data from the data warehouse to the data lake and the other way around. So I was 2 years at AWS before. And then when I started at Databricks, we had, it was in the middle of the pandemic, we did a virtual fireside chat with my ex-colleagues from AWS. And I said, hey, you have your data warehouse, Redshift, let's name it. And if you do, tell me really, honestly, if you do data science machine learning, are you running this directly on a data warehouse? And I know all those databases, they do a little bit of machine learning. Some of them can forecast some values in a table. So it seems possible, like if you do those tick marks for the comparison matrix, they often say, we do it. I said, are you doing this? And they said, no, typically what we do is we export from Redshift, we put it in a S3 bucket, and then we run our notebooks. I say, yeah, that makes sense. But they copy from here to here. And sometimes, because people want to use those, BI tools and SQL analytics and whatever, they copy the other way around. So you duplicate data, you don't know what's the source, and things become more complicated. On a governance level, we just had a security talk. How do you enforce security in a meaningful way across two different systems? It's almost impossible because on the data lake side, you have your S3 buckets and IAM rules, which are cloud specific again. And on the data warehouse side, you have your SQL tables. It just doesn't work together. So that's hard. The governance part is hard, and then the two different teams and two different skill sets. So what we propose is, well, that's the Databricks Lakehouse, but I like to explain it's more a general concept. It's an architecture, a platform. And if you Google, like AWS talks about the Lakehouse, Oracle talks about the Lakehouse, Snowflake talks about the Lakehouse. So we're kind of happy that we pioneered this, this view, but now we're also super happy that people take over this concept. Now, the idea is it should be simple, one system instead of two. So like one team instead of two, unified approach for governance, and one common storage layer. It should be open, based on open source, based on open standards. And remember how I started the talk when I said there's this specific solution for people using 1 million cores. Now our solution is multi-cloud. And then people say, so what does it mean, multi-cloud? Multi-cloud means just pick your cloud and run it wherever you want. And I mean, negotiate the hell out of your cloud provider and tell them, if we get it there cheaper, can't you match the price for this one? So just pick it. Streaming data. The Lakehouse supports streaming data. We'll go into more details. It's actually streaming ingest. It's streaming ETL. ETL is typically the core thing that data engineers do, like pipelines that do the transformation of your incoming data to some output, event processing, event-driven applications, and ML. So this is not about ML, this talk, but about all the rest. Okay, now you say, this sounds too good to be true. What's the foundation? How does it really work, such a lakehouse? The answer is it's based on open source. It's based on Data Lake. Data Lake is a thin open source layer that brings back the quality of service that you were used from your data warehouse, but you don't have it anymore in your data lake. So it kind of converts your data lake to the lakehouse. Here it says it gives you back ACID transactions. That's really cool for the database people. And I tell you in a minute why this is really cool. It's a Linux Foundation, open source project. And the people who wrote it, they published a paper in this CIDR journal. So if you're more the scientific person, you can read up the original paper. It gets 8 million downloads now per month. That's the Delta Lake. We have a lot of connectors, and the number of downloads, they kind of increase by a factor of 10 within a year. So it gets more and more popular. We're super happy about this. And obviously, it needs to integrate with all the other systems. So without the connectors, it would be too isolated. All right, so I said it's open source, what you can do on your laptop, and I sometimes start like this. I won't do it today. You just say PySpark minus package delta, and then you have your Delta Lake environment that gives you this additional layer and converts your data lake into the lakehouse with all these additional benefits that I like to explain a bit more. Talking about Spark, this is how we started, you know. I said, hey, it's so cool to read in multiple JSON files with multiple data sets per JSON file, and I don't know how many, and it just works. What if I want to convert such a JSON structure to Delta? Well, I say data frame, write, format Delta, and that's it. So if I start with this PySpark package Delta, oops, the next thing I can do is write, format Delta, and that's it. Now, the cool thing is, from then on, I have a lot more functionality. Like when I was so excited at the beginning, I said, look, we read in those files, and we have a data frame, and we select all the customers that drive a particular car. The excitement stops when you realize that with the original approach, you couldn't even do a simple update. So for the database people, you couldn't do a merge. So it's just kind of read-only, and then it stops working, unless you have a more appropriate underlying storage layer, which is Delta. So with Delta, you can do updates, you can do merges. You can actually do a lot more. I put it here in SQL syntax because this is the easier way to fit it on one slide. But remember, you can do the same thing using data frames. So update, upserts. There's a way of doing time travel. You could create a table and then say, well, update everything, update all the email addresses to hello@test.com, and then you realize, oh God, I changed all the email addresses for the whole table, and then you just time travel back one version, and you have your original data. Or you screw up and delete everything or whatever. You can always go back in time, because this is how the storage format works. We have clones, shallow clones and deep clones. Deep clones copy your data. Shallow clones are more like a pointer. There's a table history, obviously, because it incrementally writes those, tempted to say delta changes. This is kind of easy to remember why it's called delta. And there's special ways of, co-locate data, get rid of old data. Because of the versions, you can say just retain the last 12 hours. So all this is possible, and now it seems more like a database again, your data lake, doesn't it? And it makes more sense for the data warehouse people. Now, typically, the next question is, what I get here is like, hey, Frank, now we understand you kind of figured out a way to get the data warehouse quality of service into a data lake, but does it really perform? I mean, that's the other thing. Having something built with a lot of effort and then it doesn't scale, well, it doesn't help, It doesn't help for your enterprise-grade data warehouse. Well, it does scale. It's basically two things that make it work. One is a serverless approach. So you don't manage clusters for this SQL part. It's zero management. You get instance elasticity because basically the database connections are kind of pre-confined. It works like a Java database connection pool, like the same principles. And because it scales instantly, you get a lower total cost of ownership. So this is the serverless part. The other part is we spend a lot of time in making this faster. So we kind of took the Spark API and re-implemented this for modern processors. So it's kind of a vectorized C++ execution engine that works without you seeing that at all for Spark. So all the updates you do and all the writes you do, they go through this photon, which is the optimized Spark layer. This is the jump in performance, and the numbers that you see are the Databricks version. So it starts with 2, 3, 4, 5, and then you see this jump, like Databricks version 8 was that much performant, and then with Photon, it had this huge jump. Now we are at 12, but you can always add Photon or not add Photon, and you get this additional performance boost. And then people say, okay, that's still like how you did it, but how efficient is it? And we participated in this official TPCDS benchmark. It's a huge data warehouse benchmark with different workloads, 100 terabyte size workloads. And I think we won against the previous record by a factor of 3 in performance. And if you look at performance per cost, it's a factor of 12. So it's much, much cheaper. And even if you don't care about the money, it's still faster. Okay, but now coming back to streaming, and this is what I wanted to talk about. Well, if you want to do streaming within the Lakehouse, you can do streaming the normal way with Apache Spark, and also streaming data analytics, where you have these win-node functions and you group and average over the last minute or 10 minutes. And I'm going to show you an example about this later. Okay, now we have all the building blocks, and now I think we need a good quote. And who's always good for a good quote? Gregor Hope. He said, you should architect for abstractions and not illusions. So having all those building blocks, how would you make the life of a data engineer easier? And that's kind of what we want to do as a company. Like, should they go back to use Spark Structured Streaming together with Delta Lake? Well, I think no. There could be easier things. First of all, is streaming ingest. Like, if you write on the back of an envelope in kind of programming style syntax, how would you ingest streaming data? I would write something like this. You ingest from a location, which is this one, and you want to have these JSON files. If you write this in a Databricks notebook, what happens is, behind the curtains, if it was running on AWS, but you don't even care, if it was running on AWS, it would create an SNS notification that is triggered by new files. It would put those files in an SNS queue that it would create, and then it would read those files with an exactly once semantics, and all this you never see. If you do the same thing, it happens behind the curtains on GCP or Azure. And this is why I typically tell people, now guess where I'm doing this demo, and they can't guess. So this is like this, the high level, well, this is working code, but this is like as easy as you could specify it. And this is like streaming ingest from JSON files. We use it a lot, 5 petabytes a day. There's a second thing, talking about data pipelines. How would you write a data pipeline the easiest way? Well, you need to create a table. The system we use, it's called Delta Live Tables. And it's a way to specify batch or streaming data pipelines in a declarative way. So you write SQL, but you don't say insert the data. You only define the tables and how they depend on each other. Here you see one raw data table. It's actually using the autoloader, which says read the files from raw data, it's JSON files, and get them all. This is ingesting all the files in a streaming way. And then in the second table, which is called clean data, we go back to raw data and we say, read this live from raw data. And the second clean data table is also a streaming table. Now we can do this because Delta, the Delta storage format supports streaming. You can stream to a Delta table and you can stream from a Delta table. So the underlying storage format is suitable for streaming, for inserts and for reads. Now, high-level view, what can you do? If you have streaming ingestion, it typically either comes from a messaging system like Kafka or Kinesis or a socket, or, and that's the other interesting thing, you could read in a streaming way from a folder, like from a S3 bucket where constantly files or objects are put in. We have two different ways of doing this. Then you can process it with a high level, what I showed you, Delta Live tables, which is the SQL abstraction of writing a data pipeline in the easiest way possible. Actually, DLT also works with Python. If you want to use Python, you can use Python. I'll show you an example about that as well. Or you go back to Spark Structured Streaming that, well, still exists. The underlying storage format is Delta Lake because it's very useful. We can stream to it. We can stream from it. And then you have your data consumers on the right-hand side that consume this data. I have two demos. One is just slides, and the other one I want to show you. The slides one is, how much time do I have? Still 15 minutes. 15 minutes, that's fantastic. So I don't need to rush. So we should talk about this stuff any longer, I think. I always tell my colleagues, don't bring Corona data, because like we're all so sick of seeing this Corona data. Now, I bring you not Corona data, but even a simulator that I wrote. Now, the complete story to start at the beginning. At the beginning of the pandemic, a group of German scientists said, look, there was patchy outbreaks from people coming back from skiing and people celebrating those carnival parties. And there were like 2 locations in Germany with these outbreaks. And then scientists said, wouldn't it be cool if we could measure those outbreaks as early as possible, because if people get sick, they get the fever. Now, you can't measure, how would you measure fever in 80 million people in the German population? You can't. But the thing is, if you have a fever, your heart rate goes up. Actually, your resting heart rate goes up, to be more precise. Now, how would you measure heart rate in millions of people? The answer is here. You walk around with heart rate monitors. Now, this is Germany. You can't just intercept the data. They had to ask for the data. This is why it's called Data Donation Project. So they said, are you willing to donate your heart rate data? And then please install the app, which connects to your Apple Watch or whatever. And then we collect the data, and we try to see if we can use the data to early predict those outbreaks. I mean, now we're not talking about early predicting outbreaks anymore. But this is the result. If you see the red curve is the positive ones. And actually, before they get tested, the heart rate, the resting heart rate, already goes up. So it would be a suitable system for detecting those outbreaks. And this is what they used to kind of create such maps. And when I wrote a simulator that kind of simulates the IoT data, puts it in a Kafka queue, and then uses our technology to process the Kafka queue in a streaming data pipeline. And I talked about this like 3 times, maybe at conferences. And then this happened. Like here, let me think about it. This peak, I had a glass of wine with a friend. And then the next day, nothing happened. And then this day, I started sneezing, and I thought, like, that's weird. Like, it's a strange feeling. And I did a test for fun, and, well, it was positive, like, first time, like, December last year. And then I felt worse, and I felt worse. And then I called my manager and said, I'm so sick, I can't work anymore. And then I continued to feel bad, but slightly better. And then, actually, here, I said, I'm feeling good again. And this was the first time I tested negative. So that's coming from my Fitbit. So what sounds like a very theoretical story, and I told a theoretical story, and I wrote this simulator, same thing happened to me. And I was like, this curve resting heart rate really matches like how I felt. And to be honest, after this, it went up and down a little bit. Yeah. So what I did is I wrote a simulator that generates the data. I don't have it here now, but I'm telling you. It writes the data to a Kafka queue. Then in the next step, how do you get all the data out? How do you process it? How do you drop the data, the events that don't make sense? If you have a zero measurement, You don't want to have, people without a heartbeat, etc. And all this was done in Delta Life tables, actually in Python, the Python version. Minus 10? No, 10. Minus 10. Oh, okay. Hang on, sorry, now I'm confused. Okay, so all this was done and processed, and then at the end I used Spark Structured Streaming to do real-time data analytics with whatever you can do with Spark Structured Streaming. But the cool thing is, it starts like this. It starts like Spark, read stream, format Kafka, subscribe to that topic. And that's the first way to create such a Delta Life table. What you do is you say def, you define a function, you add this decorator, DLT table, and then you have your first Delta Life table. And then you can create a second one that depends on the first one. You select the columns that you want, etc. Now, the second demo is a completely different story. What I wanted to do is ingest streaming data from a real data stream from Twitter. And I take the Twitter data stream and I put it in an S3 bucket. And a lot of people say, why are you doing this? I say, well, all people, they use S3 as a data lake. They put stuff in a data lake. And then I need to read from this data lake using Delta Life tables again. And this is Delta Life tables in SQL, and that's what I want to show you. So that's actually the first notebook that is using the Tweepy API. It's a Databricks notebook, so this is where I could switch from Python to SQL or whatever. So this is using Tweepy. It's connecting to Twitter. It has a search term defined that says like Delta Life tables, Databricks, Vox days. If I tweet something like Vox days, you can tweet if you like, because this is really live. Vox days loves Delta Life tables, and I add some. Let's add some emojis because then it's easier to see this. This is not well done, but I run this notebook. I just say run all. It's connecting to Twitter. It tries to filter a live Twitter stream of data. Go for these keywords. It takes English, German, and Spanish tweets, and it's running this command. It's actually waiting for a tweet. So if you would like to tweet something, you could help me, but you don't have to, because I prepared this like a professional. Let's tweet. Okay, that's the tweet with all these funny emojis. Let's look at this. Here it comes. Look at this. That's the live tweet. It would take this tweet. Now, in the notebook, I can define, do you want to write every single tweet, or you want to combine 50, 100, or 1,000 into one object in a S3 bucket? But it ends up in the S3 bucket. Then in the next step, I have my streaming ingest. We like to call it bronze, silver, gold medallion architecture, where we incrementally improve the data quality. So this is bronze. It reads a JSON file from this file. It reads everything. In the next step, I have a silver table. In this silver table, I have a constraint that improves my data quality. I say, look, the thing I want to do later is machine learning and automatically classify those tweets in positive or negative. And the machine learning model only works with English tweets. So I can drop rows that are not suitable, and I can also drop columns, because in Twitter I get like 40 different columns in Tweepy API, and I only take over those 4. So I incrementally improve my data quality. This pipeline thing I can obviously run. I was running this before I came in here to be better prepared, and it read like 6,900 tweets. And this is a streaming data pipeline. So if I run this again, and I'm trying to do that, let's see here. Yeah. It needs to wait for this resources. Okay, let's keep this running. I come back to this. I'll show you the output. So I wanted to, the whole purpose of why I'm doing this is because I wanted to automatically classify those tweets. So I have a Hugging Face transformer, which is a pre-trained ML model to classify tweets. It's importing the transformer, and then I have a pipeline. Now, this is the interactive one, where I have like the smiley face and the I love Lakehouse. If I try and classify this, it is positive with this probability and positive with this probability. And let's add one more to show you that this is really live. Something that is not positive, like, you're all Java programmers, no? Let's have a out of memory exception. Positive or not? What do you think? Good or bad? Depends. It's neutral. Okay. Tell me something bad, but not really bad because this is recorded. No. It needs to be something that your grandma understands. Like, I don't know. I don't know if car accident works. I should prepare this better, but accident. It's also neutral. Let's say it's about sentiment. I don't like this. Look at this. It's negative with 96%. And so you see, this is the analysis is working. Now I scroll up just to show you what's happening. I'm reading the output of the pipeline, which is a delta table. Remember, it's the table I can stream to and stream from in delta format, convert it to pandas. I run it through this Hugging Face transformer, and then at the end, I create a list of most positive tweets. So I select for label positive, I sort it by score. So this is 96% positive, whatever they tweeted. And then I can do all the typical gimmicks. I can create a word cloud, or I can say, look, I mean, basically, let's be honest, we were looking for Databricks products and VoxD together, and 13 plus 66, that's 79% positive or neutral. That's not bad, I would say. And I was using this a while, so there's a lot of rubbish data in it as well. And with this, I always want to conclude the presentation. Okay. Both demos I have on GitHub, so if you want to play with them, you're super welcome to play with them. They're on GitHub. For the streaming ingest from Kafka, I wrote a blog posting. It's on Databricks blogs if you want more details. There's a lot of cool things because also think I tell you about we ingest from Kafka in a streaming way. Kafka has a retention period of, how long, do you know? 7 days, I think, is the default. And then your data is gone. And yeah, well, what we want to do is, remember I told you, we want to kind of give you the data warehouse quality of service on your data lake. So we don't want to have the data disappear. And if you refresh such a data set and it would reread everything from Kafka, it might miss some data. So we have settings that we say, okay, for reading from systems with a short retention period, don't refresh those tables. Keep the old data, but just add new data. That's one thing. There's a lot of resources. Actually, all these slides are online on Speaker Deck. And now I want to do one more thing. Go back to here, to here. Look at this. Isn't that beautiful? Remember, this was like 6,900, and I told you it's streaming ingest. The definition of streaming ingest is it's stateful. If you run it again, it's not rereading everything again. It's just automatically adding whatever came up in between. So there were 5 tweets that showed up between I was running this before the session, and if I click on start, again, it will incrementally only read those tweets. Now, these are tweets, and you think like, why would I care? Normally, this is what you do in a batch way, but you could do it in a streaming way. And in a batch way, remember how often your batch jobs for ETL went wrong and you had to fix it, like half of the data was included. Now with the Delta Lake, you have asset transactions. With Delta Live Tables, you have this easy way of creating batch or streaming data pipelines, and they work incrementally. Isn't that cool? That's the end of my talk. Thank you for being here and chat with me over coffee or over lunch. Thank you.